Hello, and thank you for joining me today for our discussion on conservation of energy. So we've talked about mechanical energy, we talked about which is made of potential and kinetic energies. Today we're going to talk about the conservation of energy. And so imagine a roller coaster. And if you've been on one, you may have noticed there's a conveyor belt on the bottom. But in terms of energy, the conveyor belt is the most important part because once you start out, that conveyor belt gets you to the top of that first hill. So all the energy required for the ride comes from the work done by the belt as the cars go up the first hill. Okay, so once you get to the top of that first hill, you have all the energy you're going to need. The energy from that work is stored as gravitational potential energy because you are way up in the air. After that, most of the energy goes through a series of transformations or changes, turning into kinetic energy and then back to potential energy again. We're going to kind of look at this and talk about this today. Okay, so a small quantity of the stored energy is transferred to the wheels, this heat. So if you would feel the tracks after the cars go by, the roller coaster track itself would be kind of a little bit warmer because of that friction, along with the air, and that's the roaring sound. But most of it, a lot of it, goes to that kinetic energy. So energy readily changes form from one to another. So readily changes from one form to another. But whatever form the energy takes during a transformation, the total energy is always the same. That's this conservation idea. So conservation of energy is the total amount of energy will always remain the same. We'll talk about that in a couple slides here. But this, for example, if you have your potential energy here is 354 kilojoules. I have no kinetic energy because I'm at the very top. My height is 70 meters. As I go down the hill, the potential energy changes into kinetic. Because I'm getting closer to the ground, I'm losing my potential energy. My height's decreasing. But as I do that, I'm speeding up, so my kinetic energy is going up. When we get to this small little ridge, we get to this small little ridge. This is half the height of this one. So 70 meters is this height, 35 meters is this height. That means that half of this energy is going to still be potential, which is 177 kilojoules. The other half is going to be kinetic. So now my kinetic went from 0 to 177. My potential went from 354 to 177. This is what we're going to kind of talk about with conservation of energy. And so with this, potential can become kinetic. That's absolutely possible. On the flip side, kinetic can become potential. But almost all the energy of the roller coaster is potential energy at the top, at the top of the first hill. So those tracks get you up to the top of that first hill. And if you've ever paid attention, you'll notice that most of the time, this hill is going to be the biggest. Because once we get up there, we have all the energy we need, and from there, the roller coaster runs itself. At the bottom of the lowest hill, so we get clear down to here, most of that energy is going to be kinetic, and the least amount will be potential. So here I'm going to be going the fastest. Up here I have the most potential. Okay, and so this changes as you go down the hill. So the closer you get to the ground, the more kinetic you're going to have. The higher up you are, the more potential you're going to have in terms of a roller coaster. But you'll notice that the system, the roller coaster itself, kept the same amount of energy the entire way through, aside from the little bit we lost to friction. So all the GPE at the top changes to kinetic energy as it goes down the hill. And when it reaches the lowest point, it has no gravitational potential left. So at the lowest point, you run out of your potential energy because you can't get any lower. If all the energy were to remain as mechanical, then the increase in kinetic energy would be equal to the decrease in potential energy. In this case, it's not perfect because of friction, but we can simulate it on the computers, and we can show you kind of what that looks like. Okay, so we said potential can become kinetic. Kinetic can also become potential. So when the car is at the lowest point, it has almost all kinetic energy. And this is what's going to do the work to carry you back up another hill to have potential energy. As you go up, so as the car climbs this track, it's going to slow down, which means my kinetic energy is going to decrease. But as it does so, notice I'm gaining height here. My height's going up, which means that I'm gaining potential energy again. So this is energy being converted from one form to another. At the top of the smaller hill, you have some kinetic energy because you're still moving, but you'll also have some potential because you're now above the ground also. And as long as, so the question of the kinetic energy will carry the car over the next hill. That's the point. I go up this hill, I go down, I go up the next hill, and I go down. As long as this hill number 2, is not taller than hill number 1. What happens if I had a bigger hill here? What happens if this was my second hill? Well, if I only had this much energy to start with, I can only go up that high. And so I won't make it to the top. I won't have energy to get clear to the top, and I'll have to start over or hook to a conveyor belt again to get back up to the top. So that's what happens if we put our hills out of order. Mechanical energy can change to other forms of energy as well. So we can go from GPE to KE all the time, and the height of the ball would be the same. If there was 100% transformation, you would drop a ball and it would come to the same height every time. But it doesn't, because some of that energy is transferred to sound. That's why you hear a ball drop. It also would heat the floor up a little bit. If you had a thermometer that measured micro increases in temperature, you would notice the temperature changes as well, because when you hit those molecules, they move faster, and temperature measures the average kinetic energy, the average moving energy of the particles. So that's going to be a higher temperature. So even though the ball continues to bounce, it loses some of that energy and bounces a little bit lower each time, and eventually won't bounce at all, just like with your roller coaster. Okay, here's some questions for you to answer. This is kind of a mid-section pause. I'm going to continue on, but you can pause it here and answer these questions. So where does a roller coaster car have the greatest potential energy? Where does it have the least potential energy? Given the graph over here, actually using this graph for all of these. So where's the greatest potential energy? Where's the least potential? Given this, can we calculate the car's speed? If we had just this data, could we calculate the car's speed? And what does this graph show you about the relationship between potential energy and kinetic energy? So what happens to those two when they work together? All right, and then I'll continue on here. The last bit we're going to talk about is called the law of conservation of energy. And this is basically the statement that we're basing everything else on. And this statement is that energy cannot be created or destroyed, only transferred from one form to another. I should have added that in there. Only transferred from one form to another. So I can't make or destroy it, but I can change it to a different form. So the total amount of energy in the universe never changes. It may go from one form to another, but the total amount of energy is always going to be there. It has to be there somewhere. So when fireworks explode, the chemical energy transfers to light, heat, and sound. That's how fireworks work. All the energy is stored in these chemicals, in these bonds, and then it's released, and that's what we see as fireworks. Light energy can be transferred as work or heat. So for example, lifting a ball gives it gravitational potential energy. And lifting it, you are exerting a force and moving it over a distance. So by exerting my force upward and I reach this distance, that would be my work. And so for any system, the net change in energy equals the energy transferred as work and as heat. So this can get kind of ugly. It can get really complicated, but scientists like to look at smaller systems or areas of energy. So a system where energy and matter are exchanged is called an open system with the surroundings. If they're exchanged with the surroundings, it's called an open system. For example, water vapor leaving boiling water. But if energy and not matter is exchanged, it's called a closed system. So in this case, we had water leaving. So an isolated system has no exchange of energy or matter. If it's closed, we're only exchanging energy. But these are some ways that we can look at energy transformations. So one place we see this is we look at dams. So a dam is made to create this storage of water here. And so you have this energy stored in the water here. As it goes down, so there's potential energy here. As it goes down, it produces kinetic energy, which then turns a turbine, which is attached to a magnet, which produces electricity. And then this water goes from a higher potential energy to a lower potential energy and exits out the bottom. And so this is how dams work. And we take advantage of water having energy due to its position here and the change in altitude from the top to the bottom. That's how dams work. That's one place we use this and see this at use in our everyday lives. So here's another one. This is the Three Gorges Dam in Asia. So water is built up here. Notice that this reservoir is much higher than the exit chute. And so by water flowing and turning these turbines, turning this generator, we're producing electrical energy that can be transmitted outwards. And so we took this potential energy that's stored up here and converted it to kinetic energy and then eventually to electrical energy over here before releasing the water back down. And so because we didn't take any water out, the water is still there, which is good. So water is discharged back into the river, so we didn't lose any water, but we were able to produce some energy from it, which is kind of nice for us. Okay, and the last little bit we're going to talk about. So with that, only a portion of the work done by any sort of machine is useful. And that's the work that the machine is designed to do. Because we have this thing called friction. Friction, heat, and sound are the biggest forms of energy that lessen the machine's useful work, that make things not as effective. So efficiency measures how much useful work a machine can do. It's measured based on percentages, and no machine has 100% efficiency because of this thing called friction. So some of the energy is going to be lost to heat, and that's the friction side of things. You might hear sound as well, but that is why we don't have 100% efficiency. The more efficient you are, the better your return on your work. So the more work that you put in actually goes to what you want it to. So then you also need energy inputs, and so we're putting energy into a machine in order to get different energy out. And the more efficient you are, the better that conversion is. All right, this was the conservation of energy and the law of conservation of energy. I would like you to answer question 1, question 2, and let's do 3 and 4. You should be able to answer those, and we'll call that a day. But make sure you can answer those questions when you see me next, and I will talk to you next time.